Venus formed from the same material as Earth at roughly the same time in the same neighborhood of the Sun, and for possibly 1 billion years it had liquid water. Subscribe if you want more of the cosmos. This is white space settled in 4.5 billion years ago. A world took shape in the inner solar system that, by every measure available to physics and chemistry, should have become something like Earth. It had the right mass. It formed from the same population of rocky planetesimals in the same neighborhood of the early Sun, under the same gravitational rules. If you had observed the solar system during those first few 100 million years of planetary assembly and been asked to predict which world would eventually host oceans, a temperate climate, and perhaps even life, you might have pointed to Venus. You would not have been unreasonable. Today, Venus registers a surface temperature of around 465 degrees Celsius. That is hot enough to soften lead. The atmospheric pressure at the surface is equivalent to being submerged nearly a kilometer beneath the ocean. The clouds that permanently shroud the planet are composed primarily of sulfuric acid droplets, and beneath them the sky glows a dim, rust-colored amber, the filtered remnant of sunlight struggling through nearly 100 kilometers of dense carbon dioxide. Nothing we have ever sent to the surface has survived longer than a couple of hours. And yet, for all of this, Venus is not simply a failed world. It is a world that diverged. That distinction matters enormously, because understanding how Venus became what it is may be the most important question in planetary science today. Not because we want to colonize Venus, but because what happened there is almost certainly the same thing that could happen to any rocky planet of similar size orbiting a star similar to our Sun, including planets we are discovering around other stars. Including, if we are careless about the long-term future, Earth itself. The story of Venus is not a story about catastrophe arriving from outside. No asteroid collision explains it. No nearby stellar explosion rearranged its chemistry. The mechanisms that made Venus uninhabitable were already present at its formation, embedded in the ratio of its distance from the Sun, the mass of the atmosphere it accumulated, and the inexorable brightening of the star it orbited. Venus destroyed itself slowly by degrees over geological time, using only the physics available to any ordinary rocky planet. That is what makes it so worth studying and so difficult to look away from. To understand the divergence, you have to start at the beginning. Venus and Earth formed at roughly the same time, from roughly the same raw materials within a few tens of millions of kilometers of each other in the protoplanetary disk that surrounded the young Sun. The disk itself was a structured thing, with a temperature gradient that determined what could condense and accrete at any given orbital distance. Close to the Sun, temperatures were too high for water, ice, and volatile compounds to survive in solid form. The inner planets therefore formed primarily from refractory materials, silicates, iron, nickel, and other compounds with high melting points. Venus, at 0.72 astronomical units from the Sun, sits slightly inside Earth's orbit. The difference in raw material was not dramatic. Both planets ended up with similar bulk compositions. What differed from the very beginning was the energy budget. Venus receives about 1.9 times the solar energy per unit area that Earth does. In the early solar system, when the Sun was roughly 70% as luminous as it is today, that number translated into more manageable surface temperatures. Models suggest that the young Venus may have maintained surface conditions cool enough for liquid water for somewhere between a few 100 million and 2 billion years. The uncertainty in that range reflects genuine ignorance. We have not been able to date any surface feature on Venus to the early epoch, because the surface as we see it today was largely produced by volcanic activity that erased the prior record. But the physics of water stability and early solar luminosity is robust enough that the possibility of an early habitable Venus is taken seriously by planetary scientists. It is not a fringe idea. It is a standard part of the discussion. The water itself likely arrived the same way it arrived on Earth. During the period of late accretion, when the inner solar system was still being pelted by asteroids and comets drifting inward from more distant orbits, water-bearing material rained down on the terrestrial planets. Some of it was absorbed into the mantle during the molten phase. More was delivered by subsequent impacts once the surface had cooled. Earth retained that water. It formed oceans. The oceans drove a carbon cycle that regulated atmospheric carbon dioxide levels, drawing down the greenhouse gas and storing it in carbonate rocks on the seafloor. That regulation kept temperatures stable through enormous variations in solar output over billions of years. It is one of the reasons Earth has remained habitable as long as it has. Venus may have had a version of this system. Some models suggest a shallow global ocean, or at least regions of standing water, persisting through the first billion years or more. These are not deep oceans like Earth's. The models favor a shallower body of water, perhaps a few hundred meters on average in the lowland basins, fed by outgassing from the interior and sustained by a climate that, while warmer than Earth's present-day average, remained below the boiling point. The atmospheric chemistry of early Venus in these models looks, at least in broad terms, like a warmer and more humid Earth. Carbon dioxide was present, but so was water vapor, which influenced how carbon was cycled and how the atmosphere responded to changing solar input. If the ocean hypothesis is correct, Venus had a functioning water cycle for hundreds of millions of years. It had rain, it had evaporation. It had the continuous exchange of material between atmosphere, ocean, and rock that on Earth produced the chemical conditions necessary for life. One line of evidence that anchors this picture comes from the inventory of nitrogen in the Venusian atmosphere. Both Venus and Earth have roughly similar total amounts of nitrogen relative to their masses. On Earth, most of that nitrogen resides in the atmosphere. On Venus, the same is true, despite the enormous difference in total atmospheric mass. This similarity suggests a common origin for the nitrogen in both planets, and it is consistent with a history in which Venus initially outgassed a nitrogen-rich atmosphere similar to Earth's, rather than one dominated from the beginning by carbon dioxide. The subsequent accumulation of carbon dioxide on this reading was not original, but acquired through a specific chain of events that Earth avoided. The collapse, when it came, was not an event. It was a transition, playing out over millions of years as the sun slowly brightened. As more energy arrived at Venus, surface temperatures rose. Higher temperatures allowed more water to evaporate. Water vapor is itself a greenhouse gas, more potent per molecule than carbon dioxide in certain wavelength ranges, and its addition to the atmosphere drove further warming. The oceans shrank, then vanished. As the oceans disappeared, the mechanism that had been removing carbon dioxide from the atmosphere through rock weathering and carbonate deposition stopped working. Carbon dioxide began accumulating. The warming accelerated. This is the feedback loop that defines the runaway greenhouse effect, and on Venus it ran to completion in the upper atmosphere, exposed to the full intensity of solar ultraviolet radiation without the shielding that the magnetic field and ozone layer provide. Water molecules were broken apart. The oxygen atoms that resulted were reactive and were absorbed into the rocks of the surface. The hydrogen atoms, being extremely light, were accelerated by the solar wind and escaped to space at a rate that, over billions of years, removed the remaining water entirely. This process, called hydrodynamic escape, has been confirmed by measurements of deuterium in the current Venusian atmosphere. Deuterium is a heavy isotope of hydrogen that escapes more slowly than ordinary hydrogen. The ratio of deuterium to ordinary hydrogen in the Venusian atmosphere is roughly 150 times higher than on Earth. That enrichment is exactly what you would expect if Venus once had large quantities of water and lost it preferentially through atmospheric escape over long timescales. The absence of a magnetic field accelerated this loss considerably. Earth maintains a strong global magnetic field generated by convection in its liquid iron outer core. That field deflects the solar wind, the continuous stream of charged particles flowing outward from the Sun, and protects the upper atmosphere from being stripped away. Venus has no such field. Its interior appears to generate at most a negligible induced magnetic field through interaction between the solar wind and the ionosphere. The reason for this absence is not entirely settled. One leading hypothesis connects it to the planet's extraordinarily slow rotation. Magnetic field generation in planetary interiors depends on convection in a liquid metallic core. But that convection must be influenced by planetary rotation to produce a coherent, large-scale field through what is called the dynamo mechanism. Venus rotates only once every 243 Earth days. That is so slow that the Coriolis forces organizing core convection may be insufficient to sustain a working dynamo. Without a magnetosphere, the upper atmosphere of Venus was exposed directly to the solar wind throughout its history. Charged particles from the Sun could penetrate the ionosphere and energize atmospheric gases enough to escape. The rate of water loss would have been significantly higher than on a magnetically shielded planet. The combination of extreme solar irradiance and magnetic nakedness meant that once the feedback began, the water could not be retained. The carbon dioxide that accumulated in the aftermath now constitutes about 96.5% of the Venusian atmosphere. The remaining fraction is mostly nitrogen, with trace amounts of sulfur dioxide, argon, and other compounds. The total mass of the Venusian atmosphere is about 93 times that of Earth's atmosphere, and nearly all of that mass is carbon dioxide. This is not a gas with powerful molecular vibration modes at every relevant wavelength, but there is simply so much of it that it absorbs and re-emits thermal radiation with extraordinary efficiency. The surface of Venus is in thermal equilibrium, not with the energy arriving from the Sun, but with the energy trapped within an atmospheric column of almost crushing density. It is as if the planet is sealed inside an industrial furnace, and the furnace has been running for hundreds of millions of years without pause. Standing on the surface of Venus, were it physically possible, would be a profoundly disorienting experience. The light level is roughly equivalent to an overcast day on Earth, despite the Sun being closer. Most of the solar radiation that reaches Venus is reflected by the cloud deck, which has an albedo of approximately 0.65, meaning it reflects 65% of incoming sunlight back to space. The fraction that penetrates is scattered and absorbed as it passes through nearly 100 kilometers of increasingly dense atmosphere, so that by the time it reaches the surface, it arrives as a dim, diffuse orange-tinted illumination. There are no shadows. There is no direct sunlight in any recognizable sense. The sky above is not visible. It is simply the underside of an impenetrable cloud layer glowing faintly with the diffused light of a star, 108 million kilometers away. The atmosphere near the surface is nearly motionless. The terrifying winds of the cloud layer, hundreds of kilometers per hour at 60 kilometers altitude, decay rapidly with decreasing elevation. At the surface, wind speeds are typically a few kilometers per hour, a gentle breeze by Earth standards. The problem is the density. At 90 atmospheres, even a slow-moving gas exerts considerable force. The surface wind would feel more like moving through water than through air, and the temperature, of course, is uniform and permanent. There is almost no day-night temperature difference at the surface of Venus. The Sun takes 117 Earth days to cross the Venusian sky from east to west. and the atmosphere is so efficient at distributing heat that the surface temperature at midnight is within a few degrees of the surface temperature at noon. The furnace is always on. At higher altitudes, an entirely different world exists. The atmosphere of Venus is stratified in ways that took decades to fully characterize. The lowest layer, from the surface to about 50 kilometers, is the troposphere, and it is within this layer that most of the mass of the atmosphere resides. It is hot, dense, and largely cloud-free below about 48 kilometers. Above 48 kilometers, the clouds begin. They are organized into 3 distinct layers. The lower cloud layer, from approximately 48 to 52 kilometers, consists of larger sulfuric acid droplets, some mixed with other sulfur compounds whose identities remain uncertain. The middle layer, from 52 to 57 kilometers, is the densest and most optically thick part of the cloud deck. The upper layer, from 57 to about 70 kilometers, grades into a haze region that extends several kilometers higher still. Each layer has its own temperature structure, its own photochemistry, and its own wind regime. The chemistry within these cloud layers is not fully understood. Sulfur dioxide rising from the lower atmosphere undergoes photochemical oxidation near the cloud tops, producing sulfur trioxide and sulfuric acid. The sulfuric acid condenses and falls as droplets, which eventually evaporate in the hotter lower atmosphere, releasing sulfur dioxide again and completing a cycle. What is less understood is the origin of a broad ultraviolet absorption feature visible in images of the Venusian cloud tops. This absorption gives the cloud deck its distinctive banded appearance in ultraviolet light, with dark streaks running along the low latitude regions and lighter areas at higher latitudes. The identity of the absorber has been debated for decades. Ferric chloride, elemental sulfur, and various other candidate compounds have been proposed, but none has been definitively confirmed. It is possible that the absorber is biological. It is also possible that it is a form of sulfur chemistry that has not been adequately modeled. Without direct sampling, the question remains open. It was within this complex atmospheric system that the Soviet program attempted to gather data, and eventually, with remarkable ingenuity, succeeded. The final major Soviet initiative at Venus was not a surface lander at all. In December 1984, the Soviet Union launched the 2 Vega spacecraft toward Venus, with an additional destination, Halley's Comet, which was approaching the inner solar system in 1986. Each Vega spacecraft performed a Venus flyby and released a descent module. But the descent module was divided into 2 components, a standard lander and something entirely new, a balloon aerostat designed to float in the Venusian cloud layers for as long as its battery power lasted. The 2 Vega balloons deployed in June 1985. Each was about 3.5 meters in diameter when inflated and carried a gondola with instruments measuring temperature, pressure, wind speed, light levels, and the presence of cloud particles. The balloons floated at an altitude of approximately 54 kilometers, within the middle cloud layer at a pressure equivalent to about half an Earth atmosphere and a temperature of roughly 40 degrees Celsius. Warm but not lethal by any measure. Each balloon traveled nearly 9,000 kilometers across the planet over 46 hours before its batteries failed, carried by the super-rotating winds of the cloud layer. Ground stations on multiple continents tracked their signals through very long baseline interferometry, constructing detailed wind velocity measurements along each trajectory. The Vega balloons provided the first in situ measurements of wind structure within the Venusian cloud layer, confirming the superrotation and revealing turbulent, variable conditions within the clouds that no orbital observation could have detected. They were a scientific achievement that the international community celebrated across political divides at the height of the Cold War, and they remained the only balloons ever flown in the atmosphere of another planet. The Soviet space program understood almost none of Venus's character when it began sending spacecraft there in the early 1960s. The planet was, to the scientists of that era, a plausible candidate for life. Beneath those clouds, which prevented any optical observation of the surface, almost anything seemed possible. Some researchers proposed a planet covered in swamps and primitive vegetation, warmed by a moderate greenhouse effect. Others imagined a global ocean beneath the clouds. The scientific community's uncertainty was genuine and in some ways understandable given how little data was available. The first Soviet attempt to reach Venus launched in February 1961. Venera 1 lost contact with Earth about 2 months after launch and passed within approximately 100,000 kilometers of Venus without returning useful data. The subsequent years produced a long series of attempts, many of them failures never publicly acknowledged in the Soviet Union. Spacecraft were lost on the launch pad, failed to leave Earth's orbit, lost contact during the cruise phase, or arrived at Venus and were destroyed almost immediately on entry into the atmosphere. The pattern of failure was informative in retrospect. Each spacecraft that managed to return data from the descent confirmed that the atmosphere was far denser and hotter than expected. Each new mission was redesigned to handle conditions that the previous mission had discovered by being destroyed. Venera 4 in October 1967 became the first spacecraft to transmit data from within the atmosphere of another planet. It returned temperature and pressure readings as it descended under parachute, measuring a composition of 90 to 95% carbon dioxide and temperatures climbing steadily. The spacecraft was crushed before it reached the surface. The data from Venera 4 was so surprising that there was initial debate among Soviet scientists about whether the readings could be correct. Venera 5 and 6, arriving in May 1969, confirmed the measurements of their predecessor. By 1970, Soviet scientists had a reasonably accurate model of the Venusian atmosphere. 96% carbon dioxide, surface pressure around 90 atmospheres, surface temperatures somewhere above 450 degrees Celsius. Any romantic notion of a habitable Venus had been completely extinguished. Venera 7, launched in August 1970, was designed to survive. Its descent capsule was built from titanium rather than aluminum alloys, pressure tested to 180 atmospheres, nearly twice the expected surface pressure. Some scientific instruments had to be removed to accommodate the structural demands of survival. The mission nearly failed anyway. On entry into the atmosphere, the parachute system failed partially. A telemetry failure reduced the data stream to temperature readings only. When the capsule hit the surface, it bounced and came to rest at an angle that pointed its antenna away from Earth. Controllers received a weak, almost undetectable signal for 23 minutes after landing. It was only months later, during careful reanalysis of the data, that scientists confirmed what they had received. The temperature at the surface was 475 degrees Celsius. The pressure was approximately 90 atmospheres. Venera 7 had done what no machine had done before. It had transmitted data from the surface of another planet. Venera 9 and 10, arriving in October 1975, carried cameras capable of returning panoramic images from the surface. The photographs showed angular dark basaltic rocks, sharply fractured and largely unweathered. The rocks looked fresh. This was itself a scientific finding. Either the surface was geologically young, or the environment was paradoxically gentle on exposed rock. Later analysis favored the former interpretation. Venera 13 and 14, reaching the surface in March 1982, represented the highest point of the Soviet program's scientific capability. Each lander carried 14 scientific instruments, including a mass spectrometer, a gas chromatograph, an X-ray fluorescence spectrometer, a microphone, and a drill capable of extracting soil samples for analysis in a sealed chamber. The landers were designed for a surface lifetime of 32 minutes. Venera 13 survived for 127 minutes, Venera 14 for 57. Both returned color panoramic images and analyzed the soil as basalt similar to oceanic crust on Earth. The microphone on Venera 13 recorded the only audio ever captured on the surface of Venus: a low, persistent resonant hum, the sound of the planet's atmosphere moving across the instruments. That recording remains unique. No subsequent mission has stood on the surface of Venus. The photographs taken by Venera 9, 10, 13, and 14 remain the only photographs ever taken from the Venusian surface. There is something worth pausing over in that fact. The Soviet program, with technology that would seem primitive by modern standards, accomplished something that has not been repeated or surpassed in more than 4 decades. The reason is cost and engineering difficulty. Building a spacecraft capable of functioning in 465-degree heat under 90 atmospheres of corrosive pressure is extraordinarily demanding. Every component must be either passively shielded from the environment, actively cooled, or designed from materials that tolerate conditions more extreme than the interior of a high-pressure industrial autoclave. The Soviet engineers solved this problem with approaches that were genuinely inventive, and the solutions were expensive. And by the mid-1980s, the program had redirected resources to other priorities. The question of how the planet arrived at its present rotation adds another layer of strangeness to an already strange world. Venus rotates not just slowly but backwards, in retrograde relative to most of the solar system. Its day is 243 Earth days long, while its year is only 225 Earth days. This means that on Venus, the solar day, the time from one sunrise to the next, is approximately 117 Earth days, because the retrograde rotation partially offsets the orbital motion around the Sun. A Venusian sunrise is not in the east. The Sun rises in the west, moves slowly across the sky over nearly 2 months of Earth time, and sets in the east. No other planet in the solar system produces this effect. The origin of this retrograde rotation is genuinely unsettled. One class of models proposes that Venus formed with a prograde rotation similar to Earth's and was subsequently flipped by a large impact or a series of smaller ones during the late heavy bombardment period. Another class of models suggests that gravitational torques between the dense Venusian atmosphere and the solid body of the planet, acting over billions of years, gradually slowed the original rotation and eventually reversed it. The atmospheric torque mechanism is particularly interesting because it is an ongoing process, meaning that the current rotation rate of Venus reflects an equilibrium between tidal forces from the Sun acting on the solid body and thermal tidal forces from the Sun acting on the atmosphere. If true, this would mean that Venus's rotation is not a simple legacy of its formation history, but is actively maintained by atmospheric dynamics right now. That has implications for any model of Venus's climate evolution, because the rotation rate influences the atmospheric circulation, which in turn feeds back into the torques that determine the rotation rate. The system is coupled in ways that are difficult to separate. Magellan, the American spacecraft that entered Venusian orbit in August 1990, mapped more than 98% of the Venusian surface using synthetic aperture radar over 4 years. What those maps revealed was a world of enormous geological complexity. The surface is dominated by vast volcanic plains, highland regions called tesserae, and thousands of distinct volcanic features. Among the most unusual are structures called coronae, large circular or oval features ranging from a few hundred to over 1,000 kilometers across, surrounded by concentric ridges and fractures. More than 500 coronae have been identified on Venus. They appear to form where rising plumes of hot material from the mantle push upward against the underside of the lithosphere, causing it to dome upward, fracture, collapse, and generate volcanism around the perimeter. On Earth, similar plume activity produces hotspot volcanoes like Hawaii, but the lack of plate tectonics on Venus means the plume cannot be bypassed by a moving plate. Instead, the plume interacts with the lithosphere in place, producing the corona structure as the lithosphere flexes and eventually relaxes. Coronae represent a form of mantle surface interaction that has no precise Earth analog and has been studied almost exclusively through the lens of Magellan radar imagery. Their three-dimensional structure, their interior compositions, and whether any of them are currently active are questions that current data cannot answer. The shield volcanoes of Venus are enormous by any standard. Mount Mons, the highest volcano on the planet, rises approximately 9 kilometers above the mean surface elevation and spans hundreds of kilometers at its base. Its radar-bright lava flows extend for enormous distances across the surrounding plains. Sappas Mons, another large shield volcano in the Atla Regio highland region, shows evidence of multiple overlapping lava flow episodes. In 2023, reanalysis of Magellan radar data by a team at the University of Alaska revealed direct evidence of active volcanic change on Venus. Two radar images of the same volcanic vent, taken 8 months apart during the Magellan mission, showed a change in the shape and size of the vent that is most plausibly explained by a volcanic eruption or vent collapse during that interval. This was the first direct observational evidence that Venus is volcanically active in the present epoch, confirming what many scientists had long suspected based on the freshness of lava flows seen in radar imagery and the presence of elevated sulfur dioxide concentrations in the atmosphere above certain volcanic regions. The global volcanic resurfacing that the Magellan data implied was one of the most striking findings in planetary science of that decade. The crater count on Venus is low, and on a planet with no erosional processes capable of removing impact structures, a low crater count means a young surface. The current best estimate is that most of the Venusian surface was produced by volcanic activity between 300 million and 700 million years ago. Whatever was there before was buried. This could mean that Venus undergoes periodic catastrophic resurfacing events where heat builds up in the mantle over hundreds of millions of years until the lithosphere becomes unstable and overturns globally. Or it could mean that ongoing distributed volcanic activity continuously refreshes the surface at rates that happen to produce the observed crater density. Distinguishing between these interpretations requires data that Magellan could not provide. The impact craters that do exist on Venus offer additional information about the resurfacing question. Unlike the Moon or Mars, where craters come in all sizes down to the smallest that can be resolved, Venus has very few small craters. The reason is the dense atmosphere, which ablates and breaks up small impactors before they can reach the surface intact. Below a certain size threshold, an incoming rock is destroyed in flight, and only a dispersed field of fragments reaches the surface, producing a distinctive radar-bright cluster rather than a clean impact crater. Above the threshold, impactors survive and produce normal craters. This atmospheric filter means that the Venus crater population represents only the larger end of the impactor size distribution. And the statistics are therefore somewhat harder to interpret than on airless bodies. Nevertheless, the spatial distribution of craters provides a constraint. They appear to be distributed essentially randomly across the surface, with no strong preference for older or younger terrain in any obvious spatial pattern. This is more consistent with the episodic global resurfacing model than with a model where resurfacing has been ongoing and spatially variable, though the question is not definitively settled. The tesserae, the ancient highland regions that rise above the volcanic plains, may hold the key to the pre-resurfacing history of Venus. The word tessera means tile in Latin, and the name reflects the complex tile-like texture of these regions in radar imagery, produced by multiple overlapping episodes of tectonic deformation in different directions. The tesserae are topographically high, which means they have likely survived the volcanic flooding that buried the lowland regions during the resurfacing event. They may therefore be the oldest terrain on the planet, potentially preserving rock that formed before the catastrophic volcanism that reset the geological clock elsewhere. Whether the tesserae formed in an earlier epoch when Venus had liquid water and whether they contain minerals diagnostic of aqueous alteration are questions of enormous importance. Some researchers have proposed that the tesserae are analogous to continental crust on Earth, buoyant material that rises above the denser volcanic plains because of its composition. If the tesserae formed under conditions that included liquid water, they might contain hydrated silicates, carbonates, or other water-altered minerals. Detecting such minerals from orbit requires sensitive infrared spectroscopy in wavelength windows, where the atmosphere is transparent enough to allow surface emission to reach orbit. This is precisely what the Veritas mission has been designed to attempt. More recent analysis of Magellan data has identified regions in the lowland plains, where large blocks of the lithosphere appear to be in motion relative to each other, sliding, rotating, and colliding in patterns that resemble a fractured ice sheet. Some blocks appear to have moved recently enough to deform features that formed after the main global resurfacing episode. If that interpretation is correct, parts of the Venusian surface are geologically active today, not through plate tectonics in the Earth sense, but through a mobile, fragmented lithosphere driven by convection in the mantle below. This finding connects to one of the most fundamental questions in comparative planetology. Earth maintains its habitability partly through plate tectonics, which drives the carbon-silicate cycle. Venus, as we observe it today, lacks this system. But if Venus had some form of lithospheric mobility in its early history, when it also had liquid water, it may have had a version of this regulation. The loss of water did not just eliminate the oceans, it eliminated the mechanism that kept the atmosphere in check. One phenomenon associated with Venus's interior that has been debated for decades without resolution is the question of lightning. On Earth, lightning is a consequence of charge separation in convective clouds containing ice particles and liquid water droplets. The Venusian cloud system is rich in convection but lacks water in any form that would support the standard electrification mechanism. Nevertheless, multiple Soviet probes detected electromagnetic signals during their descents that were interpreted as lightning discharges. The Cassini spacecraft, during its 1998 and 1999 flybys of Venus on its way to Saturn, detected radio emissions consistent with lightning at low rates. The Venus Express Orbiter, operated by the European Space Agency from 2006 to 2014, detected what appeared to be Whistler waves in the ionosphere above Venus, a type of electromagnetic phenomenon that on Earth is produced by lightning strokes below the ionosphere. The Akatsuki spacecraft has searched for optical flashes from lightning but has not detected any convincing events. The issue remains unresolved. If Venus does have lightning, the implications for atmospheric chemistry are significant because lightning discharges can drive chemical reactions that produce compounds not otherwise present in equilibrium atmospheric chemistry. Understanding whether Venus has lightning, and if so, what kind and at what rate, is relevant to understanding the overall atmospheric chemistry budget. The European Space Agency's Venus Express mission, which operated from April 2006 until the spacecraft exhausted its propellant in late 2014, represented a major scientific contribution in the 8 years between Magellan and the new missions. It carried an infrared spectrometer, an ultraviolet and visible imaging spectrometer, a magnetometer, a plasma and energy analyzer, and a radio science experiment. It studied the atmosphere continuously over nearly 8 years, covering multiple Venus years and building a statistical picture of atmospheric variability that no previous mission had achieved. Venus Express confirmed and extended the understanding of the South Polar Vortex, a persistent atmospheric feature centered roughly over the South Pole that was already known from earlier observations. Polar vortices on Venus are different from their Earth equivalents. They are not single coherent structures, but contain inner vortices that change shape and position over timescales of days. The southern vortex observed by Venus Express had a complex figure 8 or S-shaped inner structure that precessed around the pole over a period of several Earth days. Understanding how such a structure is maintained in the Venusian atmosphere, given the overall superrotation dynamics, is a problem in atmospheric fluid dynamics that has not been fully resolved. Venus Express also measured the rate at which hydrogen and oxygen are being lost from the top of the Venusian atmosphere to space. The measurements confirmed that Venus is continuing to lose whatever trace amounts of hydrogen remain in its atmosphere, mostly in the form of hydrogen ions accelerated by the solar wind. The ratio of hydrogen loss to oxygen loss was not equal to 2:1, which is what simple water dissociation would predict. Oxygen was being lost at a higher rate than the water dissociation chemistry alone could account for. This implies that additional sources of atmospheric oxygen are being swept away, consistent with ongoing volcanic outgassing that contributes to the atmospheric inventory. The measurements from Venus Express provided a snapshot of the ongoing atmospheric evolution of Venus, confirming that the planet is not in equilibrium but is still changing, still losing material, still being reshaped by the interaction of its atmosphere with the solar wind. Critically, Venus Express also returned evidence of recent volcanic activity, predating the more definitive 2023 Magellan reanalysis by about a decade. The spacecraft detected elevated sulfur dioxide concentrations in the upper atmosphere, early in its mission, followed by a decline over subsequent years. The pattern is consistent with what would be expected from a major volcanic eruption, a pulse of sulfur dioxide injected into the stratosphere, gradually consumed by photochemical reactions over the course of years. This kind of temporal variation in atmospheric chemistry was not something that any previous mission had been in a position to detect, because no previous mission had maintained continuous observation of the Venusian atmosphere over a period of years. Venus Express also identified regions of elevated thermal emission from the surface in certain infrared windows, which some researchers interpreted as recently erupted lava flows that had not yet cooled to the temperature of surrounding older terrain. The upper atmosphere of Venus presents a different kind of complexity. While the surface bakes in still heavy air, the cloud layers 50 to 70 kilometers above the surface are in constant rapid motion. The entire atmosphere rotates around the planet in approximately 4 Earth days, a phenomenon called superrotation. The planet beneath it rotates only once every 243 Earth days, and in the opposite direction to most planets in the solar system. The atmosphere is moving roughly 60 times faster than the solid body it surrounds. The winds in the upper cloud layer reach 360 kilometers per hour. The mechanism that maintains this superrotation, continuously accelerating atmospheric gas to speeds far exceeding the planetary rotation rate, is a fundamental problem in atmospheric dynamics that remains incompletely understood. The Japanese spacecraft Akatsuki, which achieved Venusian orbit in December 2015 after a technical failure had prevented its planned 2010 insertion, has been observing the cloud layers across multiple wavelengths for years. Its infrared cameras can peer into the lower cloud layers in ways that previous orbiters could not. One of its more striking findings was a stationary bow-shaped structure in the upper atmosphere, stretching over 10,000 kilometers from pole to pole, persisting for days in nearly fixed position relative to surface topography, despite the superrotating winds. This is a gravity wave in the atmospheric sense, a wave generated when horizontally moving air is forced upward over a topographic obstacle. On Venus, the scale is planetary and the mechanism is still debated. Because the surface features large enough to generate a wave of that scale are not clearly identified. One atmospheric phenomenon visible in the Magellan-era radar data, subsequently confirmed by multiple missions, is the presence of bright radar reflective material coating the peaks of high-altitude mountains on Venus. The Venusian highlands, at elevations above roughly 2,600 meters, show anomalously high radar reflectivity. For decades after Magellan, this feature was debated. The proposed explanation that has gained the most traction involves metallic sulfide compounds, specifically bismuth sulfide and lead sulfide, which have high radar reflectivity and known volatility at temperatures relevant to the Venusian surface. At lower elevations where temperatures exceed 465 degrees Celsius, these compounds are in gaseous form and cycle through the atmosphere. At the higher, cooler elevations of the mountain peaks, where temperatures may be 30 or 40 degrees lower, they can condense and deposit on the surface, producing a metallic snow. This is not water ice, it is a metallic condensate forming and accumulating in slow motion on the highest ridges and summits of Venus, while the lowlands bake under conditions that keep it in vapor phase. The phenomenon is a striking illustration of how the extreme conditions on Venus produce processes that have no Earth analog, even though they operate by ordinary chemistry and physics. In 2020, a group of astronomers announced the detection of phosphine in the Venusian atmosphere using radio telescope observations. Phosphine on Venus was immediately significant because the conditions on Venus are so chemically oxidizing that producing phosphine through known non-biological chemistry is extremely difficult. On Earth, phosphine in the atmosphere is produced almost exclusively by biological processes. The announcement generated intense interest and considerable controversy. Subsequent reanalysis of the data showed that some of the signal attributed to phosphine could be explained by sulfur dioxide, which is abundant in the Venusian atmosphere and has overlapping spectral features. The consensus shifted the phosphine detection was likely a measurement artifact, not evidence of atmospheric chemistry that defied geological explanation. But the episode demonstrated how little we actually know about the detailed chemistry of the Venusian cloud layers, and how much those layers are still capable of surprising us. The cloud layer between roughly 48 and 60 kilometers altitude is, in certain respects, the most Earth-like environment in the solar system outside of Earth itself. The temperature at cloud top altitude is approximately 30 degrees Celsius. The atmospheric pressure is close to one Earth atmosphere. The energy flux from the Sun is comparable to that received at Earth's surface. This has led some researchers to propose that if life ever took hold in the Venusian atmosphere during a more hospitable period, it might have survived in the clouds as the surface became uninhabitable, adapting over billions of years to chemistries that no Earth organism uses. Aerial biospheres are not without precedent. Earth's atmosphere contains viable microbial cells at altitudes of tens of kilometers. The question is whether the cloud layer of Venus, with its sulfuric acid droplets and highly oxidizing chemistry, could support any biochemistry at all. current opinion is skeptical, but the question is taken seriously enough to warrant direct investigation. On Earth, microbial life has adapted to sulfuric acid environments. Extremely acidophilic organisms thrive in volcanic hot springs and acid mine drainage systems. The relevant question for Venus is not whether sulfuric acid is inhospitable to life as we know it in moderate concentrations, but whether the specific physical and chemical conditions in the Venusian cloud layer could support any biochemistry at all. The difficulty is that sulfuric acid is also a powerful dehydrating agent, and life as we understand it requires water. The aerosol droplets in the Venusian clouds contain some water, but the activity of that water is extremely low. Most astrobiologists regard this as a near insurmountable obstacle, but near insurmountable is not the same as impossible, and the cloud layer of Venus remains one of the more unusual environments in the solar system where direct measurement of atmospheric chemistry could settle the question more firmly. NASA's Da Vinci mission, currently in development for a launch in the early 2030s, will address some of these questions directly. The mission profile involves releasing an instrumented descent sphere into the Venusian atmosphere. As it falls toward the surface over approximately an hour, the probe will sample the atmospheric composition at multiple altitudes. The specific focus is on the lower atmosphere below the cloud layer, where no spacecraft has made careful compositional measurements since the Soviet missions of the 1970s and 1980s. Noble gas abundances will help constrain the history of the atmosphere. How much was delivered from the original planetary material, how much came from volcanic outgassing, and how much has been lost to space. The ratios of different isotopes of argon, krypton, and xenon carry signatures of different delivery and loss processes that cannot be confused with each other. Understanding those ratios will allow planetary scientists to reconstruct far more precisely than is currently possible how the Venusian atmosphere has evolved over the planet's lifetime. Da Vinci will also image the Tessera terrain during its descent because the probe's final trajectory passes over a highland region called Alpha Regio. The cameras will have a spatial resolution finer than anything Magellan achieved and will return the first close-up images of Tessera geology. If the tesserae contain minerals diagnostic of aqueous alteration, the spectroscopic instruments on the probe may detect them during the descent. The tessera observations are in some ways the highest stakes scientific objective of the entire mission, because the results could either confirm or rule out the hypothesis that early Venus was wet enough to produce hydrated minerals in significant quantities. The Veritas orbiter will map the surface at far higher resolution than Magellan achieved. Its synthetic aperture radar will produce topographic maps accurate to a few meters in elevation. It will carry an infrared spectrometer capable of measuring surface composition in certain near-infrared spectral windows where the lower atmosphere is transparent enough to allow surface emission to reach orbit. This will allow scientists to distinguish between different rock types across the surface and potentially map the distribution of materials diagnostic of ancient weathering under wetter conditions. If early Venus had liquid water at the surface, some minerals formed in that water may still be present in the highlands, preserved from resurfacing and detectable from orbit. The European Space Agency's Envision mission, intended to arrive at Venus in the mid-2030s, complements these American missions with a different instrument package. Working in coordination, the three missions represent an investment in Venusian science that has no precedent since the height of the Soviet program. The questions they address collectively span the full range of the outstanding scientific problems: atmospheric composition and its history, surface composition and its relationship to geological processes, the interior heat flow and its connection to volcanism, and the ongoing interaction between the atmosphere and space. Each mission provides data that the others cannot, and their overlapping observation periods will allow direct comparison of results obtained by different instruments and different methods. What drives that investment, beyond the inherent fascination of Venus as a world, is the increasing urgency of understanding how rocky planets maintain or lose habitability. Over the past 3 decades, astronomers have discovered thousands of exoplanets. A substantial fraction are rocky worlds with radii between 1 and 2 times Earth's radius. Many orbit in or near the habitable zones of their stars. We cannot characterize their atmospheres in detail with current instruments, but the next generation of space telescopes will begin to do so. When we look at the spectrum of a rocky exoplanet's atmosphere, we will need to know what we are looking at. We will need to know what the planet at the inner edge of the habitable zone looks like after a runaway greenhouse event. Venus will be our reference point. The TRAPPIST-1 system, discovered in 2017, offers a particularly urgent context. 7 rocky planets orbit an ultra-cool dwarf star 40 light-years from Earth, and 3 of them fall within the conventional habitable zone. The innermost of the potentially habitable planets, TRAPPIST-1e, receives a stellar flux comparable to what Venus receives from our Sun. If it has an atmosphere, the question of whether it is in a Venus-like runaway greenhouse state or a potentially habitable state is one of the most important questions in contemporary astronomy. The James Webb Space Telescope is already attempting to characterize the atmospheres of the TRAPPIST-1 planets through transmission spectroscopy, a technique that measures which wavelengths of starlight are absorbed as the planet passes in front of its star. The signal is faint, the measurements are difficult, and the interpretation requires detailed models of how different atmospheric compositions produce different spectral signatures. Those models are calibrated against known cases. Venus is a known case. This is not a metaphor. When astronomers attempt to model the atmospheres of temperate rocky exoplanets, they use the same physics they apply to Venus. The runaway greenhouse threshold, the hydrogen escape rate, the ratio of atmospheric mass to stellar irradiation, these are the variables that determine whether a given planet can maintain liquid water at its surface. Our uncertainty about where exactly the threshold lies, about how long a Venus-like planet can maintain a moderate climate before the feedback becomes irreversible, is a direct consequence of our incomplete understanding of Venus itself. Every measurement Da Vinci makes in the Venusian lower atmosphere narrows the parameter space within which those models operate. It makes our assessment of exoplanetary habitability more precise. The question of what Venus might have been is not purely academic. It touches something in how we think about the relationship between a planet and the life it might support. Life on Earth has profoundly altered its own environment. The oxygen in Earth's atmosphere is almost entirely a product of biological activity. The carbonate rocks on the seafloor represent billions of years of biological carbon fixation. Earth's habitability is not purely a gift from planetary physics, it is partly a construction maintained by the biosphere it supports. This raises a question about Venus that is genuinely difficult to answer. If Venus had liquid water for hundreds of millions of years, possibly more than 1 billion years, was there time for life to originate? And if life did originate on Venus during that window, did it have any effect on the trajectory of the planet? Could a biosphere have extended the period of surface habitability by drawing down carbon dioxide? Or was the feedback from the brightening sun simply too strong for any biological regulation to counteract? We do not know. We cannot currently know. We have no direct evidence that life ever existed on Venus, and the surface conditions that would preserve such evidence were obliterated by the volcanic resurfacing event that reset the geological clock several 100 million years ago. If Venus had microbial mats covering its shallow seas 2 billion years ago, those mats are gone. Their molecular signatures are gone. The rocks they may have chemically altered are gone, buried under kilometers of lava. The question of ancient Venusian life, belongs to a class of scientific questions that are meaningful but perhaps permanently unanswerable with current technology. There is also a deeper question about time. We know with high confidence that the sun is gradually brightening. In approximately 1 billion years, the increase in solar luminosity will push Earth's climate toward the same runaway threshold that claimed Venus. The timescale is long by human standards, but it is not long in geological terms. Whether life on Earth can persist for another billion years in any form, whether it can adapt to a gradually warming world over that timescale, depends in part on understanding exactly how the runaway greenhouse process unfolds on timescales of hundreds of millions of years. Venus went through that process, the chemistry it left behind, the isotopic signatures in its atmosphere, the geological record of its surface. These are the traces of a billion-year catastrophe that we have not yet fully read. The Soviet engineers who built Venera 13 were not thinking about exoplanets or the long-term fate of Earth's climate. They were thinking about titanium alloys, pressure ratings, and thermal insulation. They were thinking about whether a particular drilling mechanism could extract a coherent soil sample in 465-degree heat without the borehole collapsing before the sample reached the analysis chamber. They were solving extraordinarily concrete and immediate engineering problems. But the data their spacecraft returned flowed into models and analyses that now inform our understanding of planetary evolution across the galaxy. Science works this way. The specific and the immediate accumulate into the general and the vast. The missions being built today carry instruments that the Soviet engineers could not have imagined, operating with computational power that would have seemed fantastical. In 1982, the questions they are designed to answer are sharper, more specific, more carefully formulated. But they are the same questions at their root that drove every mission sent to Venus since 1961. How did this world become what it is? What does it tell us about the conditions under which planets like Earth are possible? Venus suggests the margin between a habitable and an uninhabitable world is narrow. Not impossibly so, but narrow. A small difference in orbital distance, a slightly different rate of atmospheric evolution, a somewhat different balance between volcanic outgassing and chemical weathering. Any of these operating over billions of years separates a planet with oceans from a planet with a surface hot enough to smelt bronze. The solar system offered an experiment, run in parallel on two nearly identical planets, and the results were not the same. Understanding why is one of the most important things we can do with the instruments and the spacecraft and the engineering capability we have assembled. The universe does not offer comfortable answers, it offers data. Venus is one of the most important data points we have, preserved in the isotopic ratios of a desiccated atmosphere, in the radar reflectivity of metallic mountain peaks, in the ancient deformed terrain of highland tessera, in a low, persistent hum, recorded by a titanium capsule that survived 127 minutes on the most hostile surface in the solar system. Each of those measurements is a word in a very long sentence that we are only now beginning to parse. Venus has been waiting for us to pay attention. We are at last beginning to do so. The interior of Venus is in many ways the least understood part of the planet. We have mapped the surface in reasonable detail, sampled the atmosphere directly, and constructed increasingly sophisticated models of the cloud layers. But the interior, the mantle and core that drive all volcanic and tectonic activity, remains almost entirely inferred rather than measured. We have no seismic data from Venus. No lander has ever carried a working seismometer to the surface. The Soviet probes carried many instruments, but surface survival times of 1 to 2 hours were insufficient for the kind of long-term seismic monitoring that produces useful data. What we know about the Venusian interior comes almost entirely from gravity measurements made from orbit, from inferences based on surface geology, and from comparisons with Earth's interior scaled for Venus's slightly smaller size. Venus appears to have a metallic core of broadly similar proportions to Earth's core, occupying perhaps a quarter to a third of the planetary volume. Whether that core is partially liquid, as Earth's is, or entirely solid, is unknown. The answer matters because a liquid outer core is what enables the convective motion that generates Earth's magnetic dynamo. If Venus has a fully solid core, the absence of a magnetic field is explained straightforwardly. If it has a liquid outer core but generates no field, the explanation must be different. Most likely the slow rotation rate suppressing the organized convection needed for dynamo action. The mantle of Venus is almost certainly hot and convecting. The surface volcanism makes that clear. The question is what the convection pattern looks like and how it connects to the surface behavior on Earth. Mantle convection is tightly coupled to plate tectonics. Slabs of cold lithosphere descend into the mantle at subduction zones, pulling the plates along and driving the convection cells. The descending material is relatively cool and dense, and it takes heat with it. This process is extraordinarily efficient at cooling the Earth's interior and at maintaining a particular regime of surface recycling. Venus, lacking subduction, must dissipate its interior heat differently. The current hypothesis is that Venus loses heat primarily through conduction, through the lithosphere, and through volcanic eruptions that bring hot material directly to the surface. This is a less efficient heat loss mechanism, which may explain why Venus's interior is warmer than Earth's interior, and why volcanic activity has remained vigorous into the present epoch. There is a deep connection between water and plate tectonics that illuminates another dimension of Venus's evolution. Water, when present in rocks, drastically reduces their viscosity and lowers the melting point. Hydrated minerals in subducted oceanic crust release water into the mantle above the subduction zone, generating the magma that fuels arc volcanoes and lubricating the plate boundary itself. In a very real sense, Earth's tectonic system is water-powered. Remove the water from Earth's mantle, and the plates would likely lock up. The rocks would be too stiff to subduct. The mantle would be too viscous to sustain the kind of convection that pulls plates apart at mid-ocean ridges and drives them together at subduction zones. This is not a hypothetical. Some researchers argue that this is exactly what happened on Venus. If Venus lost its surface water early in its history, the water that had been incorporated into the lithosphere through weathering and ocean floor hydrothermal activity would also have been gradually driven out. A drying mantle would become increasingly viscous. The subduction zones that may have existed in an early, wet Venus would have progressively slowed and eventually frozen. The planet would have transitioned from a tectonically active world to a stagnant lid world where a single unbroken lithospheric shell sits over a convecting mantle without ever recycling into it. That transition may have been both a consequence of the atmospheric catastrophe and the cause of its completion. A world losing its water loses its tectonic engine, which loses its ability to draw down carbon dioxide, which accelerates the warming, which drives more water loss. The feedback is vicious and comprehensive. This stagnant lid regime, which Venus appears to currently occupy, is not unique in the solar system. Mars is a stagnant lid world, the Moon is a stagnant lid body. Mercury is What distinguishes Venus is that it seems to sit on the boundary between the stagnant lid regime and something more active, as evidenced by the mobile lithospheric blocks identified in the lowland plains and by the ongoing volcanism. Some researchers describe Venus as being in a transitional tectonic state, neither fully stagnant lid like Mars nor plate tectonic like Earth, but something in between that may not have an exact analog elsewhere. Characterizing this transitional state more precisely is one of the key objectives of the Veritas mission. The superrotation of the Venusian atmosphere remains one of the most puzzling features of the planet's dynamics. On Earth, the atmosphere does not superrotate because angular momentum is continuously transported from the equator toward the poles and dissipated in ways that prevent any strong net equatorial acceleration. On Venus, something maintains a persistent equatorial superrotation against whatever dissipative processes act on it. The leading mechanism involves planetary-scale atmospheric waves, specifically the interaction between thermally driven large-scale wave patterns and the mean atmospheric flow. When waves tilted in a particular direction interact with the mean flow, they can transfer angular momentum from higher latitudes toward the equator, accelerating the equatorial flow. This process, called Ghirach-Rousseau-Williams mechanism after the researchers who developed the theory in the 1970s, is broadly accepted as the correct qualitative explanation, but the quantitative details, specifically what drives the waves at the required amplitude and phase, remain subjects of active research. General circulation models of the Venusian atmosphere have made substantial progress in reproducing the observed superrotation, but they have not converged on a single definitive explanation, and the differences between models matter for predicting how the superrotation would respond to changes in atmospheric composition or stellar forcing. The broader context for all of this is the rapidly expanding catalog of rocky exoplanets. Since the Kepler Space Telescope began returning data in 2009, the number of known planets has grown from a few hundred to several thousand. Among those thousands, a significant fraction are rocky worlds, with radii between 1 and 2 times Earth's radius. Many orbit in or near the habitable zones of their stars. We cannot yet characterize their atmospheres in fine detail, but the next generation of space telescopes will begin to do so. When we look at the spectrum of a rocky exoplanet's atmosphere, we will need to know what we are looking at. Venus will be our reference point, not just as a cautionary tale, but as a precisely calibrated example of a specific planetary outcome, with a specific set of atmospheric fingerprints that we can learn to recognize at interstellar distances. The James Webb Space Telescope has already begun returning atmospheric data for rocky exoplanets. The results so far are informative in their ambiguity. Some close-in rocky planets appear to have no substantial atmosphere at all, stripped by the intense radiation of their host stars. Others may have thin secondary atmospheres produced by volcanic outgassing. The TRAPPIST-1 planets, which orbit an ultra-cool dwarf star and therefore receive less ultraviolet radiation than Venus does from our Sun, are among the most closely watched. Whether any of them has a Venus-like atmosphere is a question whose answer depends on knowing, in precise quantitative terms, what a Venus-like atmosphere looks like in transmission spectroscopy. We know the composition of the Venusian atmosphere reasonably well. We know its temperature structure, its pressure profile, its cloud structure, feeding that knowledge into radiative transfer models that simulate how the Venusian atmosphere would appear if seen in transmission from across the galaxy is a calculation that has been done. If we see a similar signature in an exoplanet spectrum, we will know what we are looking at. If we do not, that absence is also informative. The value of Venus as a comparative planetary science target is therefore not primarily about Venus. It is about everything we are trying to understand beyond Venus, across a catalogue of thousands of worlds whose diversity we are only beginning to sample. There is a version of this story that is strictly geological. A planet formed, accumulated water, experienced the feedback, lost the water, and arrived at its current state through a comprehensible sequence of physical and chemical processes. That story is correct as far as it goes. But there is another version that is harder to tell without acknowledging something that science tends to leave implicit. The early Venus, in the models that allow for a billion-year habitable window, was a world with blue skies. Not everywhere and not always, but in the models with shallow oceans and a functioning carbon cycle, the clouds would have been water clouds, not sulfuric acid. The surface would have been warm, but not uninhabitable. The chemistry of the atmosphere would have included oxygen produced by the photolysis of water vapor in the upper atmosphere. The geological record of that world, if it ever existed, is gone. Buried under kilometers of basalt, extruded in a catastrophe that lasted perhaps 1 million years. There is no surface of early Venus that we can walk across in the imagination and find familiar. It exists only in the mathematics of planetary formation models and in the isotopic ratio of an atmosphere that is itself the residue of something's destruction. We do not know if that early world was inhabited. We may never know. But the question of whether life, if it had existed on Venus, could have changed the outcome is not idle speculation. On Earth, life has extended the habitable conditions of this planet by modifying the atmosphere and the carbon cycle in ways that partially offset the increasing luminosity of the sun. Whether a Venusian biosphere, had it arisen, could have done the same depends on whether biological productivity could have scaled fast enough to draw down carbon dioxide against the accelerating feedback of a warming ocean. The physics of the runaway greenhouse suggests the feedback, once it reaches a certain threshold, becomes self-sustaining regardless of biological intervention. But whether that threshold was reached before or after life could have had a significant effect is an open question, and one that cannot be answered without knowing the timeline of the early Venusian climate in far more detail than we currently have. The missions approaching Venus in the coming decade will not resolve all of this. They will not tell us whether Venus was once inhabited. They cannot reconstruct a surface that no longer exists. What they can do is establish the chemical and geological boundary conditions within which the early history of Venus is constrained. They can measure how much water Venus began with by measuring the current deuterium to hydrogen ratio with unprecedented precision. They can map what the oldest surviving terrain looks like and whether it bears mineral signatures of aqueous chemistry. They can characterize the ongoing volcanic activity and thereby constrain the heat flow from the interior. They can measure the current rate of atmospheric escape and compare it with models of how that rate has changed over time. Each of these measurements is a constraint on the models, and each constraint narrows the range of possible early Venus histories. Narrowing that range is how science operates. It is not as satisfying as a direct answer, but it is how understanding accumulates. Venus is 108 million kilometers from Earth at closest approach. Light takes about 6 minutes to travel between the two planets at that distance. The Venera landers that returned data from the surface were transmitting across that gap, their signals already weakened by the crushing environment that surrounded them, received by dish antennas on Earth, straining to extract a coherent signal from the noise. The fact that those signals were received at all, that those temperature readings and those photographs and that hum of wind across a microphone were successfully transmitted and decoded, is a testament to engineering precision applied under conditions of genuine uncertainty in pursuit of knowledge about a world that had until that moment been entirely beyond direct observation. What they returned was the beginning of an answer to a question that humanity will be asking for as long as it retains the capacity to look upward and ask questions at all. How do worlds like this happen? And how does a world like ours avoid the same fate? Venus does not answer those questions. It is the questions written in sulfuric acid and basalt and the slow, terrible logic of a greenhouse that never stopped. Consider what it means to study a planet from Earth. The Venusian atmosphere is opaque to visible light, which means every ground-based telescope that has ever been pointed at Venus has seen only the cloud tops. For centuries, Venus in the telescope was a featureless white disk, occasionally showing phases like the moon as it moved around the sun, but revealing nothing of what lay beneath. It was not until radar technology was applied to planetary astronomy, beginning in the early 1960s, that the first hints of surface structure emerged. Early radar observations from Arecibo and Goldstone measured the rotational rate of Venus by tracking the Doppler shift of reflected radar pulses from opposite limbs of the planet, and the result was immediately surprising. The rotation was retrograde. The planet was spinning backwards. The period was approximately 243 days. These facts, established from radio signals bounced off a cloud-covered world 108 million kilometers away, were among the most unexpected results in planetary astronomy of that era. Ground-based radar also produced the first crude maps of Venus's surface, showing that it had large highland regions and extensive plains, but at resolutions of tens to hundreds of kilometers, little detail was visible. The Magellan mission in the 1990s improved on this by orders of magnitude, but even Magellan had limitations. Its radar operated at a single wavelength and in a single polarization, which means that different rock types with similar radar reflectivity at that wavelength were indistinguishable. The topographic resolution was approximately 100 meters horizontally and a few hundred meters vertically. This was sufficient to map the major geological provinces and catalog the volcanic features, but insufficient to resolve the fine structure of the tesserae to identify individual lava flow fronts precisely enough to determine their ages relative to each other or to detect surface changes between observations made years apart. The Veritas mission radar will operate at multiple polarizations and will achieve horizontal resolution of roughly 15 to 30 meters, improving on Magellan by a factor of several. The elevation precision will be a few meters rather than hundreds. At this resolution, individual features within the tesserae will become resolvable for the first time. Lava flow fronts will be distinguishable from each other. Faults and fractures too small for Magellan to detect will appear in the data. If Venus is volcanically active today, Veritas should be able to detect changes in surface morphology between observations made at different points during the mission, potentially catching eruptions in progress or documenting the cooling of recently emplaced lava. The infrared spectroscopy component of Veritas targets specific atmospheric windows where Venus's carbon dioxide atmosphere is relatively transparent, allowing radiation from the surface to escape to orbit. At wavelengths around 1 micrometer and in several other narrow bands, the optical depth of the atmosphere is low enough that an orbiting spectrometer can measure surface emission. The temperature of the surface at those wavelengths depends on both the physical temperature and the emissivity of the rock, and different minerals have characteristic emissivity spectra. Basaltic rocks have one spectrum, granitic rocks have another. Carbonate minerals, which form in the presence of liquid water through the weathering of basalt and subsequent precipitation from solution, have another. If the tesserae contain carbonate outcrops or exposures of hydrated silicates, the Veritas spectrometer may detect them. This would be direct evidence that the tesserae formed under conditions that included liquid water at the surface, which would be one of the most significant findings in the history of planetary science. The Envision mission carries a subsurface radar sounder, which is novel in the context of Venus exploration. This instrument is analogous to the Chared and Marsis radar sounders that have been used to detect subsurface ice on Mars. On Venus, the application is different. The dense atmosphere prevents the use of very low-frequency radar, which penetrates deeply into solid rock. Envision's sounder operates at frequencies that can penetrate a few hundred meters into the Venusian crust, potentially revealing the structure of layered volcanic deposits, detecting the boundaries between different lava flow sequences, and identifying buried features that the surface radar cannot see. Combined with the surface maps from Veritas and the atmospheric data from Jansky, the Envision subsurface data will allow scientists to reconstruct the geological history of selected target regions in 3 dimensions from several hundred meters below the surface to the atmosphere above. The current surface chemistry of Venus is also an active research area. At 465 degrees Celsius, the basaltic rocks of the lowland plains are in contact with the carbon dioxide atmosphere at high temperature and pressure. And the equilibrium between the atmosphere and the surface minerals is not the same as it would be at lower temperatures. Certain reactions between the hot, dense gas and the rock proceed at rates that would be negligible at Earth's surface temperatures. Sulfur dioxide reacts with calcium in the surface rocks to produce anhydrite, a calcium sulfate mineral. Carbon dioxide reacts with calcium silicate minerals to produce carbonates. These reactions draw certain gases out of the atmosphere and incorporate them into the surface rocks, establishing a chemical buffer that partially regulates the atmospheric composition. The sulfur chemistry of the lower atmosphere, which connects the volcanic outgassing at the surface to the cloud formation at higher altitudes, passes through this buffer. Understanding the surface chemistry in quantitative detail requires knowing both the mineralogy of the surface rocks and the rates of the relevant reactions at Venusian conditions. Laboratory experiments can measure the reaction rates. The surface mineralogy remains poorly constrained by current data. The combination of Veritas infrared spectroscopy and Da Vinci in situ atmospheric measurements will substantially improve both sides of this constraint. There is also a practical motivation for understanding Venus's atmospheric chemistry that goes beyond comparative planetology. The processes that govern the concentration of sulfur dioxide in the Venusian atmosphere, its production by volcanoes, its photochemical oxidation to sulfuric acid in the upper atmosphere, its removal by reaction with surface rocks, are analogous to sulfur cycle processes that operate in Earth's atmosphere, including the chemistry of volcanic aerosols that influence Earth's climate following major eruptions. The Pinatubo eruption in 1991 injected approximately 20 million tons of sulfur dioxide into the stratosphere. The resulting sulfate aerosols reduced global average temperatures by about 0.5 degree Celsius for approximately 2 years. On Venus, the entire atmosphere is in some sense a permanent volcanic aftermath, with sulfuric acid clouds that have been maintained by ongoing volcanic emissions for an indeterminate period. Studying how the sulfur budget of the Venusian atmosphere is maintained and how it responds to changes in volcanic activity gives planetary scientists a deeply detailed example of sulfur atmospheric chemistry operating at extremes that no Earth analog can match. The coming decade represents an inflection point in the scientific study of Venus. For 40 years from the end of the Magellan mission in 1994 to the arrival of Da Vinci and Veritas in the early 2030s. Venus has been studied primarily through reanalysis of existing data and through the relatively limited new observations that Akatsuki and Venus Express could provide from orbit. In that interval, the questions have sharpened considerably. The available data has been pushed to its limits. Models have been refined and debated and revised. The community of Venus scientists, which was relatively small for much of this period, has grown and diversified as the planet's importance to exoplanet science and comparative planetology has become more widely recognized. The 3 missions now in development are the product of that long period of refinement. They know what they are looking for and why it matters in ways that Magellan's designers could not have articulated, because the exoplanet era and the modern understanding of planetary habitability had not yet arrived. What will define success for this new generation of Venus missions is not any single measurement, but the construction of a coherent story. That story needs to account for the nitrogen budget and the deuterium enrichment and the tessera mineralogy and the crater statistics and the volcanic heat flux and the superrotation and the ongoing atmospheric escape. It needs to connect what we see on the surface today to what happened in the mantle hundreds of millions of years ago to what happened in the atmosphere billions of years ago when the water was still there. No single instrument produces that story. It emerges from the synthesis of many measurements interpreted through the framework of physical and chemical theory. That synthesis is what planetary science is at its best, the reconstruction of deep history from the faint signatures it has left in the present. Venus has been leaving those signatures for 4.5 billion years. Some of them are written clearly in the basaltic chemistry of a surface that volcanic activity has renewed. Some are written faintly in the isotopic ratio of an atmosphere that contains the compressed record of an ocean's disappearance. Some are written in the radar texture of highland terrain that may have witnessed a world we cannot otherwise access. Reading those signatures completely, without gaps, without ambiguity, may not be possible with any foreseeable technology. But reading them more clearly than we can read them now, building a picture that is more constrained, more detailed, and more accurate than what we have, is the work of the next generation of scientists and engineers who will build the missions, analyze the data, and extend the argument one careful measurement at a time. The planet has waited long enough. So have we